Good morning, cadets. Yesterday we learnt about motion of a charge in a perpendicular magnetic field. When a charge particle enters into a perpendicular magnetic field, or if the velocity vector of the charge particle is perpendicular to the magnetic field, then the charge particle undergoes circular motion because of the centripetal force provided by the magnetic Lorentz force, right? Now, in case if the charge particle is not perpendicular to the magnetic field, or magnetic field is not perpendicular to the velocity vector of the charge particle, then what happens? Consider a case in which magnetic field is acting along x-axis. This is x-axis and the magnetic field is acting along x-axis, and you see this is y-axis and z-axis. Think that there is a charge plus q, positive charge, which is moving with certain angle with velocity v, moving with certain velocity vector v with angle theta. The angle is not perpendicular, it is having some acute angle, let us say. Then we can resolve this velocity vector into two components. Suppose this is velocity vector, then one will be parallel component, another one is perpendicular component, v perpendicular, another one parallel component. Then when you look at it, because of the parallel component of the velocity vector, the parallel component of velocity vector is along the magnetic field, so the parallel component of velocity vector is not affected, because the parallel component of velocity vector is making an angle theta equal to 0 with respect to magnetic field. So the particle does not get affected. The parallel component of velocity vector does not get affected. Whereas perpendicular component of velocity vector will be experiencing a Lorentz force, because it is a perpendicular component making 90 degree with the magnetic field. As a result, the charge particle experiences a Lorentz force and it starts undergoing a circular motion. It will have a circular motion like this. And before it completes one revolution, it also undergoes lateral motion along the direction of magnetic field. As a result, it will have what is known as kind of helical motion. Yes, this is how the particle undergoes a helical motion. So this is helical path or helical motion of a charged particle. So here it will have a fixed radius. The radius of particle is fixed, and we know what is the equation for radius. Radius is equal to mv perpendicular upon qb, because v perpendicular is the component which is responsible for circular motion, the revolutionary motion of the charged particle, and as a result it will undergo circular motion. But it moves along the direction of magnetic field also because of parallel component of velocity vector. If v makes certain angle theta, or if angle between velocity vector v and b is theta, not 90 degree, then velocity vector can be resolved into two components. E is resolved into v perpendicular and v parallel components. V perpendicular component results into the circular motion and V parallel component results or V parallel components leads to V parallel component leads to motion along magnetic field vector B since it is not affected. Since V parallel component is not affected. Now we can calculate what is the distance covered by the charged particle in one rotation. The distance covered by charged particle in one rotation is called as the pitch. Now we know the radius is given by mv perpendicular upon qb and we have calculated yesterday the frequency of the charged particle, that is number of revolutions per second. This we have calculated. It is given by nu is equal to qb upon 2 pi m. We have derived this yesterday. So since time period is 1 by frequency, therefore time taken for one revolution is called as time period. Time period t is equal to reciprocal of frequency. So it becomes 2 pi m upon qb. 2 pi m upon qb. As a result, the charged particle undergoes circular motion. In addition, it will have lateral motion. So it undergoes a path called as helical path or helix, right? Just like a spring motion, the particle undergoes helical path around the magnetic field. Since the magnetic field is taken along x-axis, you can see the helical motion of the charged particle around the magnetic field, right? Now to calculate the pitch is calculated as the lateral distance or horizontal distance covered by the charged particle in one complete revolution. When it covers one complete revolution, you can take between this and this. What is the distance covered between two successive circular motion? That gives us the pitch. So pitch can be calculated as the horizontal distance covered in one complete revolution. So here I have calculated the distance covered by the charged particle in one complete revolution, which is called as pitch. So which is calculated as V parallel component into time period, where time period t is time taken for one complete revolution. So it is a lateral distance covered. So the lateral distance covered is because of V parallel component. So we know t equal to 2 pi m upon qb. Therefore, P is equal to 2 pi m qb, 2 pi m upon qb into V parallel component. This gives us the pitch. Okay, this is about the helical path that will be taken by a charged particle in the influence of magnetic field, right? The circular path is because of Lorentz force, and the lateral motion is the result of parallel component of velocity vector. Now it has a beautiful impact in the nature. If it is observed at the polar regions, if the sky is observed in the polar regions, magnetic north pole and magnetic south pole, you will find beautiful display of colors in the sky, like huge display of curtains or huge display of colors, colorful saris, dancing colorful saris can be observed in the sky. That is because of the interaction of charged particles with the magnetic field lines. You know, at the polar regions, this is the earth, at the polar regions of the earth, you will find maximum density of magnetic field lines of the earth. Earth behaves like a huge magnet. So, maximum concentration of magnetic field lines are observed at the polar regions, right? The charged particles which are released during the solar flares, especially the electrons and protons, after entering into the Earth's atmosphere, most of them will be trapped in the polar regions due to the maximum density of Earth's magnetic field lines. Due to these charged particles like electrons and protons, which are moving with certain velocity, they are trapped in the magnetic field with the strong magnetic field lines. As a result, they undergo the kind of helical paths which are represented here. So, during this interaction, the charged particles interact with the molecules of the atmosphere, especially the nitrogen and the oxygen. When they interact with these nitrogen and oxygen molecules of the atmosphere, these molecules are ionized and they get to the excited level, and these excited oxygen and excited nitrogen molecules release energy that is of a particular light. The excited nitrogen molecules release, excited nitrogen atoms release pink color light, pink color visible light, and excited oxygen atoms release green color light. So, as a result, you will find pinkish green display of colors, especially in the northern part of our earth, that is Greenland and Alaska, that is northern part of Canada. In the northern part of Canada, Alaska, if the sky is observed, you will find beautiful display of colors. It is called as aurora borealis. Aurora borealis. Aurora borealis happens in the North Pole. In the same way, in the southern pole also, where you find Antarctica, and close to that you will find Australia and New Zealand. So, at the southern part of Australia, you will find the similar kind of display of colors in the sky, that is called as aurora australis. If you just type in the Google or in the YouTube aurora australis or aurora borealis, you will find beautiful display through YouTube videos. Okay, you can enjoy aurora borealis in the northern hemisphere, that is in the North Pole, and aurora australis in the south pole of the earth. These are magnetic north poles and magnetic south poles. Okay, this is about the interaction of a charged particle with the magnetic field, motion of charged particle with the magnetic field, right? Okay, next we are learning very important thing, that is magnetic effect of electric current. From the Oersted's experiment, we have come to know that when the current passes through a conductor, the conductor is associated with magnetic field. Now, how to calculate this magnetic field? So, there comes a law for our help. It is called Biot-Savart law. Biot and Savart are two scientists who formulated a law which tells us about the calculation of magnetic field around a current carrying wire, around a current element, which is called as Biot-Savart law about magnetic field around a current element. Now we will discuss about magnetic field due to a current element. That is what we learn it as Biot-Savart law. Consider there is a wire XY which is having current, the current I flowing from X to Y in this way. It's a wire of some arbitrary shape. We want to find out magnetic field due to a small element of this wire, current carrying wire. You know, this current carrying wire is associated with magnetic field, right? So how to find the magnetic field due to the current carrying wire, out of which we are considering a small elementary portion of this wire and we call it as element. So when the current passes through that element, we call it as current element. The magnetic field that is produced due to this current element can be found out using the right hand rule, right? If you see, if this is the direction of current that is flowing, the thumb represents the direction of current that is flowing, then the curling of the fingers, look at this, curling of the fingers represents the direction of magnetic field. So if this is a straight conductor carrying current in the upward direction, straight conductor carrying current in the upward direction, if you hold the conductor along the thumb, then the curling of the fingers show the direction of magnetic field surrounding this current carrying conductor. If the current is flowing down, you see, if the current is flowing down, the curling of the fingers show the direction of magnetic field lines. Now it is going to be in the opposite directions. Now when the current is upward, the magnetic field lines are anti-clockwise, and if the current is flowing down, the magnetic field lines are clockwise, right? So that is how we can understand the direction of magnetic field. Then the amount of magnetic field. So using that I can write at this point the cross mark shows the direction of magnetic field. If suppose dB represents the small magnetic field due to this current element, dB is pointing vertically inwards. At the same distance, if you take here, if you take at this particular point at the other side, you see the fingers when they are entering here, from the other side the fingers are emerging out. So here you will get at the same distance you will get the dot. So here the dB magnetic field is pointing outwards and here it is pointing inwards. Here the magnetic field is vertically inwards, perpendicular to the plane of the board, right? Now how to calculate this dB, magnetic field due to current carrying conductor? It is found experimentally by these scientists Biot and Savart that the magnetic field dB is found to be directly proportional to, it is found to be magnitude, I can write magnitude of magnetic field is found to be directly proportional to strength of the current, and it is also found to be, magnitude of magnetic field is also found to be directly proportional to the length dl. And if I take the angle, so to take the angle what I do, I just draw a tangent along the current element, I draw the tangent, and this is the angle theta, with respect to the distance. P is the point at a distance r from the current element. Then this magnetic field also depends on the angle of orientation of this distance of the point under consideration. So this dB is also found to be directly proportional to sin theta, sine of angle of theta, where theta is the angle of orientation between the current element and the distance of the position, distance vector or position vector of the point under consideration. So it is one more important point, dB is found to be also inversely proportional to square of the distance, where r is the distance of the point under consideration. So clubbing all these I dl sin theta and r square, we get dB is found to be, magnitude of dB is found to be directly proportional to the product ideal. This product ideal itself is called as current element. Current element. Product ideal sin theta by r square, because it is inversely proportional to square of the distance. So this is what is known as Biot-Savart law. Biot-Savart law. When you take out the proportionality sign, we get dB magnitude equal to constant of proportionality of the medium. Here we are considering the medium to be free space, vacuum or air. Vacuum or air are being taken as free space, and mu naught is called as permeability of free space. Mu naught upon 4 pi is the constant into ideal sin theta by r square. So this becomes the magnitude of magnetic field due to the small current element ideal at a distance r. So it is inversely proportional to square of the distance, it is directly proportional to strength of the current, and directly proportional to orientation of this element with respect to the distance of the point under consideration, dl sin theta. So if theta is 0, for example, if we want to find out magnetic field along the length of the wire somewhere here, then magnetic field due to this current element along the length of the wire itself becomes 0. Reason is the angle theta in that case becomes 0. When theta is 0, obviously magnetic field is 0. Means along the direction of current element, magnetic field is 0. And magnetic field becomes maximum when this distance is exactly perpendicular to current element. When theta is 90 degree, magnetic field becomes maximum. So that's how magnetic field depends on the orientation angle theta, right? Since magnetic field is a vector quantity, we need to express this in terms of vector notation. So how to write it? Look at this. I can write this ideal sin theta as ideal vector cross unit vector r, where unit vector r is the direction of the unit vector along the position vector of the particle, along the distance vector or displacement vector of the particle, or position vector of the particle, position vector of the point under consideration, not the particle, point under consideration. So I can write the same equation as dB vector equal to mu naught by 4 pi, mu naught by 4 pi into ideal vector cross r unit vector. It is a cross, it is not into cross product. R unit vector gives you what? It is a of magnitude 1, but acting along the position vector of the point under consideration. So ideal cross r gives us ideal into 1 into sin theta. Ideal into 1 into sin theta, because magnitude of r is 1. So ideal sin theta, that's what we will get, ideal sin theta by r square. To be more specific, if you multiply this by magnitude of vector r, magnitude of vector r in the numerator and denominator, we can write the same equation dB as equal to mu naught by 4 pi into ideal vector cross r vector, because unit vector multiplied by magnitude of the vector gives you the vector itself. Ideal cross r by, here in the denominator becomes r cube. This is the another form of the magnetic field. So this gives us an idea of what is its magnitude as well as direction. So direction of magnetic field, you can see it is determined by cross product of ideal and r vector. Ideal, if you take this right hand, you see, you take the ideal along the right hand like this, right hand palm, and turn this ideal towards r vector, ideal cross r, and see the thumb points inwards. So this is right hand rule, ideal vector cross r, the thumb points inwards. That's how we get magnetic field pointing inwards. In the same way, in this case, ideal is along the length vector of the element dl vector, and this becomes the r vector here. So in this situation what happens? Ideal, see, ideal cross r, the thumb is pointing towards you, the thumb points towards you, that gives you direction of magnetic field pointing towards you, perpendicular to the plane of the board, plane of ideal and r vectors, right? That's how we get the direction of magnetic field. Now this suggests us that the cause of magnetic field is the current. The cause of magnetic field is current. Whereas in case of electric field, the cause of electric field is static charge. Whereas the cause of magnetic field is current, means motion of charges. The motion of charges lead to magnetic field. Second thing, both electric field and magnetic field, both are long range forces, right? Both are long range forces. Both are dependent inversely on the square of the distance. E is also inversely proportional to r square and dB is also inversely proportional to r square. So both are long range forces, both are depending on inverse square distance relation, right? In the case of electric field, the direction of electric field is in the same direction of electric force, whereas in the case of magnetic field and magnetic force are perpendicular to each other, right? Magnetic field and magnetic force are not in the same direction, they are perpendicular to each other. So this is how we discuss about the magnetic field, and this is called as Biot's law. And this mu naught is called as permeability of free space. Mu naught is called permeability of free space. It speaks about the medium in which we are considering the current wire or current element. It depends on the medium, right? Just like we discussed Coulomb's law, the force between two charges depends on the medium. There it is taken as permittivity of the medium and permittivity of the free space if it is vacuum. Here it is permeability of free space. How much that medium permits the magnetic field lines, that is what we call it as permeability of the medium, and in this case permeability of free space. And this value is given by 4 pi into 10 to the power of minus 7 Tesla meter per ampere. Tesla meter per ampere. Therefore, mu naught upon 4 pi, you can just remember, mu naught upon 4 pi becomes 10 raised to minus 7 Tesla meter per ampere. Tesla, you take this here, it becomes just here, you can see magnetic field is measured in Tesla. Take this r square here, it becomes Tesla meter square by current measured in ampere, and 1 meter cancels with the meter square in the numerator. So we will get Tesla meter per ampere. That is the SI unit of permeability of the medium. Now we get one interesting relation between permeability and permittivity. Just look at it, how one can relate the permittivity of free space with permeability of free space. Let us take the product of these, epsilon naught into mu naught. We know the values of permittivity of free space as well as permeability of free space. Better multiply this by 4 pi and divide it by 4 pi. Multiplying and dividing it by 4 pi, then it becomes quite easy, because we know what is 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught is 9 into 10 to the power of 9. So I will write it as 4 pi epsilon naught as 9 into 10 to the power of 9 in the denominator. 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power of 9. Therefore 4 pi epsilon naught is equal to 1 by 9 into 10 to the power of 9. And just now we got the value of mu naught upon 4 pi as 10 raised to minus 7. Very interestingly, if you take this 10 raised to minus 7 in the denominator, it becomes 9 into 10 raised to 16. 9 into 10 raised to 16. which can be written as 1 by 3 into 10 raised to 8 to the power 2. So 3 3s are 9, 10 raised to 8 into 2 becomes 10 raised to 16. And we know what is 3 into 10 raised to 8. It is nothing but the speed of an electromagnetic wave or speed of light. Therefore, we get epsilon naught into mu naught is equal to 1 upon c square, where we know c is speed of light 10 to the power of 8 meter per second is speed of electromagnetic wave. Electromagnetic wave like light means you will come to know that all the electromagnetic waves, whether it is X-rays, gamma radiations, ultraviolet radiations, infrared radiations, microwaves, radio waves, and even light, all these travel with the same speed, that is called as speed of electromagnetic wave or speed of light, which is 3 into 10 to the power of 8. Therefore, epsilon naught into mu naught is equal to 1 upon c square. This implies c square is equal to 1 by epsilon naught mu naught, or c is equal to 1 by square root of mu naught epsilon naught. So, one can find out the value of epsilon naught by the knowledge of mu naught and c, and vice versa. So, this is the relation connecting the c with permittivity and permeability of free space. Okay, thank you, have a nice day.